Okay, today we start series 8.1, sequences. And the homework involving sequences was basically you're looking at a formula that generated a sequence. So here's a sequence. And you were just trying to determine what that sequence went to, right, as n went to infinity. So all you were doing was taking the formula for the sequence and taking a limit, right? And what that did was told you the behavior of each of these. So like for this one, 1 over n, as n goes to infinity, 1 over n goes to 0. So what we know is that these numbers in this list are getting smaller and smaller and smaller and smaller. So what we're going to do now with series is totally shift gears and ask ourselves what the sum of these numbers is. All right? So given some sequence, a sub n, the series that corresponds to that sequence is the sum of the list of numbers. I don't know why I wrote if. Sorry. I meant to just say, we call this sum S. Oh, yeah, no, sorry. I said if we call this sum S. Yes, that's okay. If we call this sum S, then we have that S is equal to A1 plus A2 plus A3 plus A4 forever, right? Adding these up, dot, 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 meaning forever. This is known as an infinite series. So I'm going to add that to this, because you can have a finite series, but all we're going to be interested in are infinite series. All right, infinite. That means that our sequence had to be infinite, right? We did talk about finite sequences, but we're interested in infinite sequences, sequences that don't stop. And we're saying, all right, well, if we start adding these up, what do we get, right? Can we add these things forever? So that should already bother you. Like, how do you actually add something up forever? You can't sit there on your calculator and do it, can you? Now, you could go to some point and stop, but we're supposed to go forever. So notice the notation that I'm using here. S is the sum, right, of your sequence pieces. And we're saying that this is equal to, we've seen this notation, right? Summation. N is going to start at 1. It's never going to stop. And then what I'm doing is I'm adding up these a sub n's. A sub n is given to us. And so I'll first replace that n with 1, then add to it what I get when I replace it with 2, then add to that what I get when I replace it with 3, and then 4, and so on and so forth, dot, dot, dot. Understand? Okay, so that's just notation. Here's a specific example. If we have the sequence 1 over n, here's the actual sequence. The sum that we're looking for, the infinite series, would be 1 plus a half plus a third plus a fourth. And our question is, does that actually add up to a number or not? Or does it just get bigger and bigger and become infinite? But notation-wise, this is it. So sum n equals 1 to infinity of 1 over n, that's our formula, right? So let me continue here. That's just your example. All right, let me continue with the notes here. If the series converges, then we're going to be talking about convergence and divergence, same thing, all right? But it's a different kind of animal here because, like I said, you can't add that up forever. So let me build up a couple more ideas, and then we'll get into how we're going to do this. So another definition. This is what we call nth partial sum of a series. Okay, so what is the nth partial sum of a series? The nth partial sum is just, well, partial, it's part of the sum, it's not the whole sum. So I'm going to use, let's use a different letter here. K equals 1. Or you know what? I'll go n equals 1. And let's stop it. I'm trying to figure out what what notation I want to use. I'll use k, sorry. K equals 1 to n of a sub k. This is called the kth partial sum, or the nth partial sum. What's happening here? I'm starting out with k being what? 1. So I would replace that with 1. I get a sub 1. Plus, let k be 2, a sub 2. Next one, a sub 3. When do I stop? At a sub n. All right, so do you see that that is the nth partial sum? It only adds up the first n of these. So like if I asked for the 5th partial sum of this, it would be 1, 2, 3, 4, 5. It would be just those 5 added up, right? Understand? So with this idea of a partial sum, we can actually define what we mean by convergence of a series. A series is said to converge to capital S if the limit as n goes to infinity of sum k equals 1 to n of a sub k equals S. Okay, what the heck is that saying? This is hard to just read and understand. So what I'd like to do is work with this example again, all right? So let's take a look at this example and try and figure out what the partial sums look like. So let's try and define here. Oh, I forgot to write something here in front of this. Slow today. S sub n, sorry. S sub n is the nth partial sum that adds up your first n pieces. So if you have the capital S with the subscript n, that represents the nth partial sum. All right, so what would S sub 1 be? It would just be 1, right? You're just taking the first number, adding it to nothing itself, and you just get 1. What's S sub 2? So you're going 1 plus a half, right? You're adding up the first 2, and you get 3 halves. All right, what's S sub 3? 1 plus a half plus a third, right? And so you might have to get like common denominator here. Let's see, 6, 3, 2, I think 11 sixths. Y'all okay with that? You could get a common denominator between these. This is 6 over 6 plus, what is that? 3 over 6 plus 2 over 6. Agree? And then 6, 9, 11 over 6. So 11 over 6, right? And then the 4th partial sum, 1 plus a half plus a third plus a 4th, would just be this one plus a 4th, right? So let's do that one real quick. What's 11 sixths plus 1/4? 44 plus 6 over 24. 50 over 24. Reduce that, 25 twelfths, I believe. I'm doing this really fast, but that okay? 25 twelfths? Y'all understand what I'm doing? All right. So what we've created here is a new list of numbers, haven't we? We start out with this list of numbers, and if we start adding them up, we start getting a new list of numbers. Here's our new list. 1, 3 halves, 11 sixths, 25 twelfths, right? And if I write those in a list of numbers, I'm going to have another infinite sequence, right? This is a new sequence. Now this sequence is not the same as this sequence because it represents, it's like adding on, it's summing things up, right? So this is your first one of those added up. These are the first 2. first 3, first 4, understand? But at the end of the day, that's a new sequence. And our question today is whether or not this sequence converges. So go back to this definition. The nth partial sum is what we can use to build up a new sequence. And if a series converges, then this sequence right here, this right here, when we take the limit as n goes to infinity, it goes to some number s. Now there is something very, very problematic with this. And that's when you're doing your homework and I was saying, hey, look, take that and tell me what the limit of that sequence was. You had a formula for the sequence, didn't you? There's the formula. You let n go to infinity and you were done. Well, I mean, you had to work for it, but right? It was very clean. Here, if I'm going to take the limit as n goes to infinity, right? I'm going to let this n here go to infinity. And if this is this sum, then as n goes to infinity, doesn't the end of that sum start taking off? Does that make sense? You keep adding more terms. You don't have a nice formula for this sequence, because as n goes to infinity, you're adding more terms. This is a nice closed formula. You can let n go to infinity here. So our goal is to see if we can somehow get our heads around this right here and somehow either come up with a formula for it or get some control over it somehow. And that's generally very difficult to do. All right? So it's not going to be as simple as this. But our question is still, does this sequence converge? Does this all kind of make sense? I have some pictures I can show you with the computer to kind of give you an idea of what we just did there. Starting with the sequence, you start adding up the pieces, you get the series, that creates a new sequence. So we should really be looking at two sequences here. All right, so what I have here is I've typed in 1 over n, and I wrote this little program. I think I wrote this like 2 or 3 years ago, so let's see how it runs. On the left here, in the black, is the actual original sequence, 1 over n. Over here are your partial sums, s sub 1. So right now, I'm taking the first term of the sequence, which was 1, right? So 1, I'm up here at 1. Now I'm adding that up, and I just get 1. So here's my answer, right? When I go and I take my second partial sum, I'm going to be taking the 1 and the 1/2, adding them together and getting 3/2, right? So we come over here. This was our s sub 1. Here's our s sub 2. It's up here at 3/2, right? And I just keep doing this. And what we want to pay attention to is the sequence on the right. And let me make these points a little bit bigger so you can see them. So notice the sequence on the right and compare it to the one on the left. I think it's obvious that the sequence on the left goes to 0. We knew that already, didn't we? 1 over n went to 0. But the one on the right, does it look like it's converging to something to you? Does it look like it's getting closer and closer to some number? Or does it look like it's growing and growing and growing? Well, I actually have the sum added up for you. I've had the computer do it for you, okay? So let's just keep our eye on that. We're only at the 20th partial sum right now. We're supposed to let n go to infinity, right? So let's see what happens as I keep going out. 3.8, 3.9, 4, 4.3, right? 5. Now these points are getting a little bit too big, so let me make them a little smaller. Okay, and I can just drag this. Now I'm going to actually bring my computer to its knees here. I have to let it think for a minute. Let it catch up. This bar over here, okay, now it's caught up. I'm at the 1,788th partial sum, and I'm only at 8.066. But look at the trend of this. Does it look like it's asymptotic, like there's something it must stay under? Like, do you think there's an upper bound to this? Or do you think the further I go, it's going to overtake it? What do you think? I mean, there's no wrong answer here. Well, there is a right answer, but I wouldn't expect you to know what the right answer is. What do you think? Just what's your feel from what you see? Do you think, how many of you think it's bounded above, like it's asymptotic, okay? How many of you think that it's just going to keep growing without bound? Okay. For this particular series, 1 over n, right, or that sequence, 1 over n, that's going to grow without bound. It is going to become infinite, all right? Now, I can only try and convince you with pictures. I'm going to actually prove it to you a little bit later today. But for now, I just want you to get a visual of what's happening. Do you get it? Like what we're doing is adding up, like stacking these on top of each other, and just trying to figure out if that sum is actually going to blow up to infinity or converge to a number. So let me back this out. I better back it out way out here. Okay, 41. Let me take it down back to 1. Okay. Let's take a look at a different sequence and then look at the series that goes with that sequence and see if there's really any difference in it. So another example, let's start with the sequence 1 over n squared. And that's pretty close to 1 over n, right? I mean, this converges to 0, right? That sequence converges to 0. This creates this list. 1, then what? 1/4, 1. We're on the third one, right? 3, so 3 in there. 3 squared, 9. Now plug 4 in for n. 1/16, 1/25, 1/36, ... Okay, that sequence goes to 0, right? It converges. But what about the series? Well, the series S is going to be 1 plus a 4th plus a 9th plus a 16th plus 1/25 plus ... Now let me write this in sigma notation. Sum, I'll use n here. N equals 1 to infinity. So anytime I'm going to go from 1 to infinity, I usually put n here. If I'm going to go from something and stop, I usually go k to n instead. So here I have, what's the formula that would go in here? That would create this? 1 over n squared, right? So all you're doing is really just plugging in this formula into this summation. What do you think? Should we look at it? Should we look at the picture again? See what it does? Let's see. Yeah, so you notice that they're getting smaller faster, right? 1 over n squared gets smaller faster. They both went to 0, but this one appears to go faster. So let me come in here. I'm going to put 1 over n squared. And let me make these a little bigger so you can see them. So my first number was 1, right? And of course, if I take the first partial sum, it's just 1. The next one, if I have my second number in my list is 1/4, right? Which is right here. That's 1/4. If I take 1 and add 1/4 to it, I get, what, 1.25? Which is up here. And now I keep going. So watch on the left side as the sequence in black drops to 0. And look at the right side and look at what this blue thing does. I'm out at the 40th one, 50th one. What's your thought here? Let me drag it out. I'm going to drag it out pretty far. Let me see. I'm going to try and go out, try and see if I can get my computer to freak out. Make these as small as possible. Yeah, so this is it was growing, right? Doesn't this one look a little more asymptotic than the other one that did? Like this one looks like there's some boundary that I'm not going to get past. And I don't know what it is. Maybe it's 1.65. I'm not sure. But look, I've only gone out 1,300 numbers, right? And that's